Good evening and welcome to Igniting STEM with Computer Science, the role of computer science in engineering education. Before we get started, I just wanted to cover some bases here for housekeeping. This webinar is being recorded, but because it's in webinar format, we cannot see any of you, so do not be alarmed by that. Also, that means that if you have questions, you can type them in the chat or the Q&A feature. We will try to get to questions at the end of the webinar. And we ask that you try to keep them in there because if you send them out, we can see all of them and the participants can see your questions as well. So just make note of that. And so we're going to dive right in. All right. So I want to first start by introducing ourselves. My name is Kendall Brinson. I am a professional learning and outreach manager here in Massachusetts at the Museum of Science in Boston. I do professional development for educators across the country on our curricula products, both, yes, our Youth Engineering Solutions and EIE Engineering is Elementary. And I come to you with a host of experiences in informal education and formal education in museums and in preschool. So I'm happy to be one of your facilitators for this evening. I'll hand it to Mary.
Great, thanks, Kendall. So I'm excited to join you all today. My name is Mary Dzaugis. I work at MathWorks, part of our STEM outreach organization there. So I work a lot with K-12 teachers, educators, STEM outreach organizations, looking to introduce computational tools into school programs, out-of-school programs. I work on doing curriculum as well as activities and helping students get access to the tools that they need to get interested in STEM. I'm excited to be here with you all today.
Do that again. All right. So first and foremost, I wanted to start by demystifying some of the terms that come up when we talk about computer science. So that's the first and obvious one is computer science itself. Very, very simply, computer science is the study of how computers work and how we can use them to solve problems. Some of the other words that might come up are computational thinking. And if you Googled computational thinking, you would find something like this online. In the simplest terms, computational thinking is how computer scientists think to solve those problems. Diagrams like these really emphasize some of those hard and technical skills that computer science use to interpret, create, or refine algorithms and solve problems. So I want to break these down for you. The first one is decomposition. Computer scientists often face really complex problems, but instead of tackling the entire thing at once, they use decomposition. Decomposition really means breaking things down into smaller and more manageable parts. So think of like baking a cake. You'll think about it involves all those steps like mixing ingredients, baking, and decorating. And each of those is a smaller task within the larger goal of making the entire cake. And by focusing on each piece separately, it's so much easier to solve the whole problem. And decomposition really helps computer scientists organize and understand even the most complicated computing challenges that they might face. The next one is pattern recognition. So once you have a problem broken into smaller parts, computer scientists will look for patterns. Pattern recognition involves grouping similar things to make predictions about what will happen next. For example, if you see cupcakes arranged in the same order repeatedly, you might be able to make a pretty easy guess about what comes next. And in programming, recognizing patterns really allows us to reuse solutions for similar problems and make inferences for the future. And it also helps save time and helps us create more efficient solutions. And identifying patterns, of course, is a key skill in solving problems more effectively and efficiently. The next one is abstraction. This one typically gets students a little hung up more. So basically, not all the details are completely important when you are solving a particular problem. And that's where abstraction comes in. Abstraction involves filtering out any unnecessary information and focusing on what's really, really essential to solve the problem. So In the same vein, while I'm talking about food, imagine you're designing a recipe. Do you really need to include how the ingredients were grown? Probably not. In the computer science, abstraction helps us simplify the problems and make them easier to solve without unnecessary distractions. And of course, our favorite one, an algorithm. Finally, computer scientists, once they've done all of our other steps, might develop an algorithm to solve a problem. And this doesn't necessarily have to be on a computer, because an algorithm is very, very simply a set of step-by-step instructions that help you complete a task. So in the same vein, if you were following a recipe to bake cupcakes or cookies or whatever you like, that is also an algorithm. It tells you exactly what to do step by step. And if you did them out of order, it probably wouldn't come out exactly the way you wanted it to. So in programming or computer scientists, or computer science, the algorithms really guide computers to perform the tasks that we want them to do more efficiently and consistently, whether it's sorting data or finding the fastest route on a map. Algorithms are really how computer scientists bring their solutions to life. With all of that said, decomposition, pattern recognition, abstraction, and algorithms are all very, very essential skills for solving problems like a computer scientist. And there are others if you Google them, of course, and each plays a critical role in breaking down those tasks, like identifying trends or simplifying complexity, creating those step-by-step instructions. But these skills alone aren't all-encompassing, right? To be effective in computer science, we also need to be thoughtful and conscious users of computers and the computational tools. That means thinking beyond sort of the mechanics of problem solving and to understand the broader implications of how we use technology and what happens with the things that we create, right? So what you're seeing on the screen is the YES computer science framework, which builds on those 4 skills I just discussed by emphasizing 3 key principles. The first in blue on your screen is generate and use algorithms. And very simply, this reminds us that understanding and creating algorithms is vital in computer science. It's not just about using the tools, it's about knowing how they work and being able to create solutions. Second, in purple on your screen, is increase efficiency and accuracy. Now, this highlights that computational tools are designed to improve how we solve problems, because humans are always not perfect, right? We can make mistakes, we can make errors, and computers help us do that better, faster, and with more precision than we could over and over and over again. And finally, in the red here, which I find to be the most critical, is recognizing our social context. It's a reminder that technology doesn't exist in a vacuum, right? We need to be aware, and we want students to be aware of biases in computational tools, our own biases when we're using these tools, and consider how that impacts different groups or people or anybody who might be using the tool, and how we use and interpret data. And so by combining those foundational skills in computer science with these principles, we can solve problems more efficiently, ethically, and with awareness of the world around us. So all of our units are designed with this framework in mind. Now, you may be wondering, great, you make engineering curricula. Why are we talking about computer science? Well, to us and in our research, we know that engineering and computer science are really natural partners in solving real-world problems. While engineering might focus on designing and building a solution, computer science enhances that process by providing powerful tools for analysis or generation of those actual solutions. Right, and this is why pairing engineering and computer science in curriculum is so effective. It helps students see how the 2 disciplines actually work together in the real world to tackle real-life complex challenges. For example, you're seeing a bunch of computational tools on your screen, like sensors and data visualizations and models and simulations to design and test and refine all these creations, right? These tools allow engineers to work more efficiently and accurately, whether they're analyzing environmental data or testing a filtration system or simulating the mechanics of a car engine. So the framework we just discussed supports all of this integration all together. Like generating and using algorithms is essential for creating these tools like simulations. Increasing efficiency and accuracy ensures the tools are practical and effective, and recognizing the social context, of course, helps engineers and computer scientists consider the broader impacts of their work. By combining these principles, computational tools really empower engineers to solve problems in innovative and impactful ways. So what I want to do is hand it over to Mary to discuss some of these computational tools in real life.
Great. Thanks, Kendall. So
You're welcome.
we're going to spend a little bit of time. I'm going to introduce a new computational tool potentially to some of you today. Maybe some of you have heard of it before. And I'm first going to talk a little bit about MathWorks and what it is. And then we get to actually use the tool and see how it's used with students and how it connects really strongly with the engineering as well. So the computational tool that we're introducing today has been used by millions of scientists and engineers around the world. MathWorks created this software computational tool, MATLAB and Simulink, to help engineers and scientists do their best work. So I'm going to give a little background on these products and then share some examples of how they're used in the real world. And then we're going to jump into the Yes Middle School computer science modules, and so we can see how the students are going to be using them. And let's see. It doesn't look like I can move the slides forward. So I'm just going to pass control back to you, and I will just have you click forward.
All right, no worries. I will click.
Great. All right, so MATLAB is a programming environment that's used for algorithm development, data analysis, visualization of that data, and numeric computation. Simulink, if you click forward, is a visual programming tool that allows you to create and simulate models of real-world systems using block diagrams. It helps to make it easier to understand and test complex systems before moving to hardware, right? Which would be really expensive if you built something that was going to destroy that hardware. You want to test and make sure that it works before deploying. MathWorks has over 100 additional products for specialized tasks by engineers and scientists that might want to do things like image processing, robotics, AI, and more, but they all use MATLAB and Simulink as their base. See if you can move forward. This software is used every day to design, simulate, and test many of the products that we rely on. It's used in many automobiles, cars that you probably drive, planes that you'll fly on, in your smartphones, and even washer machines use computational tools like MATLAB and Simulink. Move forward. And engineers and scientists use our tools to develop breakthroughs by transforming the way that we live, learn, and work. So some of the areas that MATLAB and Simulink are used in are in research and design for solar-powered cars, advanced robotic prosthetics, autonomous robots, and even in clean energy, where we have wave farms that harness the power of the ocean waves to generate clean energy. And so these are just a small handful of the areas that these products are used in. And I want to dive into a few examples just to show you how these tools are being used with engineers and scientists to give you a sense of the power behind these tools. The first example is from scientists at Georgia Tech who use MATLAB and Simulink to develop this robotic prosthetic drumming hand that you see on your screen. The patient controls one of the sticks by flexing his muscles as if he were controlling the drumstick on his own with his own wrist and fingers. And the other stick, you can see that there's two, the other stick uses AI to listen and accompany to what he's playing. And after rehab and training, he has regained the lost abilities, but he can now also play faster and more complex rhythms than a typical drummer. And we have a little clip on the next screen. And Kendall, when you will click to play, and we might need to adjust that volume, it does come off very loudly, I think, the first time we play. So that was just a very quick example of sort of this life-changing application of using MATLAB or Simulink to illustrate how artificial intelligence can actually exceed human capabilities. The next example We're switching gears to something a little bit more out of this world. If we can move forward. This is an example with NASA, who uses our tools as well. So NASA's Orion spacecraft, which will carry astronauts deeper into space than ever before. The plan is through the Artemis missions to eventually travel to the moon, the asteroid, and then eventually Mars. And the Orion spacecraft is the craft that is going to be helping to accomplish all of this. In December 2014, Orion successfully launched their lunar orbit and then returned safely back to Earth. And that was sort of the first step in making sure that this is a spacecraft that can do all and accomplish all of the goals that they have. And it's sort of the first steps towards establishing that lunar base camp. So if you want to click forward, there's just a quick animation of that re-entry, and so just what that looks like. And for this, NASA used MATLAB and Simulink to develop the guidance, the navigation, and the control systems for Orion. So if you can imagine, these are very, very, very complex systems with over 20,000 different sort of scenarios that can happen, and it needs to be able to respond and act for all of those different scenarios. And so MATLAB and Simulink are helping with all of those different systems. And so in going forward, MATLAB and Simulink will continue to be used on future Artemis missions, including the planned mission for humans to get to Mars eventually. And then finally, I just wanted to share something, a little of the work that we do with some students. We work with scientists and engineers worldwide, but we also support students learning and working to become the next generation of scientists and engineers. We want to provide them with the tools and the resources that they need in order to succeed and solve the problems that they're interested in, solve the problems of our next generations as well. So we support dozens of student competitions, is just one example, worldwide each year in all kinds of fields, automotive, aerospace, robotics, all who are using computational tools to achieve their goals. And so the next little clip, this shows formula students in Germany, and we can move to the little video. We support over 100 teams. They're using MATLAB and Simulink to simulate different strategies, analyze their performance, and implement controllers. This is RoboBoat. It challenges students to develop a boat that can autonomously navigate through canals. And then RoboCup, which is a champion where students field teams of autonomous robots simulating soccer matches. And so those are global competitions where students are learning key STEM skills and using a lot of different computational tools to succeed and in their projects. So hopefully, as you could see from some of those examples, computational tools are really important parts of engineering. We wouldn't be seeing some of the achievements worldwide and the new innovations without these tools. We're going to focus on MATLAB because that's what we're going to be using with the students. And it's just computational tools are an important part of engineering, as Kendall has mentioned. They really go hand in hand, and it's hard to do engineering without computational tools. And even by the age of middle school, students start to realize the power of computers, the power of computation. And so adding these in and just starting to teach them from that young age how it can be used and how it can be used to help advance and solve their problems in a sort of reliable and in a confident way is really great. And so we're really excited to be partnering with YES on this curriculum. And so students can learn more about this and also learn about some of the pitfalls and sort of harder components that maybe they aren't always taught about using computational tools. And so these units really give students the opportunity to further explore their engineering challenges. And they interact with MATLAB live scripts in a web browser. Just we'll be seeing live scripts a lot in a little bit. Just a little background, the live scripts, it's a programming environment, it's MATLAB, but it's an environment that incorporates things like buttons, sliders, images. You can hide the code. So it's a little bit more accessible and user-friendly interface to work with the students. However, the students still have the full power of MATLAB behind it. They are using the exact same tool that the engineers and scientists at NASA are using to develop the guidance, navigation, and control systems that you saw of Orion. So it's a very powerful tool, and they are going to be using it to help look at different components of the two different engineering units that we're going to look at today. The live scripts have been designed in a way that students don't need to know how to do programming in order to complete the computer science modules. And that is a lot of what computational tools are. You don't have to be a programmer from the ground up in order to use these tools. There's tools out there that allow you to still integrate them and help solve your problems, but you don't need to be that ground-based programmer. You can use tools that others have developed. So I'm going to pass back to Kendall to give a little background, an overview of the YES middle school units, and then I'll do a deeper dive into these two computer science modules and show you what the students are going to experience.
Great, thank you. All right, so we have two public middle school units. There'll be more coming in the spring, so be on the lookout for those or sign up to be notified on our website when they go live. However, the first unit I want to talk about is one of our middle school units called Engineering Eco-Friendly Slippers. There are a few photos on the screen of some participants designing their own eco-friendly slippers. And this unit engages middle school students in designing an affordable and environmentally friendly slipper with appropriate traction. They begin by exploring the environmental impact of shoe disposal and the prevalence of synthetic materials in footwear. They investigate outsole materials to understand the role of friction and measure the force of friction between different materials and flooring surfaces. Then they apply that knowledge, and students brainstorm designs. They have to consider trade-offs among traction, eco-friendliness, comfort, and of course, cost. And then they work in teams to plan, create, test, and refine their slipper prototypes, which culminates in reflection on their engineering process and the potential impact of their designs. And after they've completed this engineering unit, there are the options for two computer science modules, one of which is user reviews analysis, which is the one that uses MATLAB, which I won't dive too much in because Mary's going to give us an awesome preview of some of the live scripts that this module uses. And the other one is step counters, which uses a microbit for students to develop, test, and iterate a step counter using an algorithm to talk about the durability of their slippers. Because of course, if it's eco-friendly, you don't want to have to throw it away every day. But let's chat about our user reviews analysis.
Great. All right, so I will share my screen. Let me, okay. All right, so we'll be looking at a few different live scripts, as I mentioned. These are all available on our website, and I'm going to actually put the link to the website in the chat in case you want to follow along on your own computer or phone. No, you do not have to. I will be going through them here, and you can always check them out later as well. So we're going to be looking at a series of live scripts that Kendall mentioned introduces machine learning, which is a type of AI, to students. Students have received reviews about the slippers they created, and they're tasked with figuring out how they can train a computer to label a review as positive or negative. So this series of scripts will take us through labeling data to create a training set, and then apply and refine a machine learning algorithm to that data to see how well the computer can do at identifying those positive or negative reviews. So the first step is we need to identify whether reviews are positive or negative, and we're going to do this manually first. So we see what it takes to be a human and go through these reviews and label this as we go. All right, so this first one here is the live script that would pop up that students would be seeing. And they go through these buttons. So this has the code hidden behind, but it runs through a series of interactions with buttons, sliders. They are fully programming and doing this as they go through the live script. So we're going to select, the computer selecting reviews for us to label. So these are some reviews that we've gotten about our slippers. Our first review is not enough traction. I slipped in them a couple of times. And so we're going to label this as a positive or negative review. Sounds pretty negative to me. So I'm going to assign negative to that label. I found them to be really slippery. These are dangerous for me to wear with floors that I have. Well, that also sounds pretty negative. So we're going to call that one negative as well. This one, great traction on vinyl flooring. And this one sounds more like a positive. All right. And then I think these slippers would be dangerous for some people. That one sounds negative to me. All right. And is there such a thing as too much traction? I thought I was going to twist an ankle. All right. That one also sounds pretty negative. All right. Great traction, great design, love them. All right. That one's positive. All right. So we've labeled all 6 of the reviews that we've been assigned. So we're going to move to section 2. So let's say that took us maybe about 1 or 2 minutes to complete. In a classroom with students, it might take a little longer. Again, there might be teams of students doing this. So let's just say there were 10 other students. We had 60 reviews total that we wanted to rate. So that would take us about 20 minutes. And yay for computers helping us check our math. We spent 20 minutes to label those 60 reviews. And so that took about 140. If we had 140 reviews, that would take us a little under an hour to complete. But thinking about those Amazon reviews online, you see sometimes tens of thousands of reviews. So thinking if we actually maybe had 1,000 reviews or 19,000 reviews to label, that would start taking us some significant amount of time, and we probably don't have the ability to do that ourselves. So this is starting to get students to think about how could a computer help us with this. And they get to look at sort of the reviews that they did positive and negative, see what other groups got as well, and just start thinking about some of the things they're seeing between these reviews. The next script, students are going to look at these reviews a little bit more closely. So let me share the next one, which is here. All right. So this next script is going to be looking at 48 reviews that were labeled by a human. So we took 48 reviews, labeled them as positive, took 24 positive, 24 negative reviews, and a human was the one that went through these. So students can look at these more closely. Label P was given for positive and label N was given for negative. And they start to look at some of the commonality and similarities between these reviews. And the computer is pulling out unique words that were identified in positive reviews and words that were identified in negative reviews. And we've decided to just say, okay, which one were used 7 times? So we want to look at the most frequent words in positive reviews and the most frequent words in negative reviews. Maybe that will help us figure out how to get the computer to notice some trends and how the computer can help us sort these later. So students will get to look at the words, and here we have a list of the positive words and negative words. All right, and so some of the things you might be noticing, well, are these the most helpful words for figuring out if something is positive or negative? Would there have been maybe other words that you would have chosen to put on this list, or ones you would have said, well, that's not a very helpful word? And so students start to discuss that and think about that a little bit more deeply. And then we have the ability to go and let's refine this a little bit more. Let's help the computer and teach the computer what to look for that might be more helpful. And so in the next script, students are going to look at these labeled reviews, identify some of the words that appear frequently in positive or negative reviews, and then refine that algorithm a little bit more. Right, so they're going to load those same reviews that they saw previously, and that these are the list of those same words. But what we've done is we've separated out and we pulled out all the common words. So in the previous script, you notice I appeared in both positive and the negative column. So now what the computer is doing is saying, okay, well, these common words, that's not helpful. We only want ones associated with positive, and we want the most frequent ones associated with negative. Right? And so now we're going to test that out. What happens when we pull out these common words and we just look at these positive ones, negative words? These are the most common words associated with the positive reviews and negative reviews minus the common. And this is what the computer got. So they have the different reviews here, how many positive words were counted, how many negative words were counted, and then what the computer guessed the label would be. So this is now the computer is guessing, the computer is applying the algorithm, and it is taking that trained data set of 48 labeled reviews and applying it to reviews that it doesn't know the answer for. All right, so what you can see here is when positive count is greater than negative account, it assigns a positive label. If the negative account is greater than the positive count, it assigns it as negative. And students start to notice, well, what's happening here with undefined, right? What happens? Why is this labeled as undefined? And hopefully what you've noticed is that is what happens when positive and negative accounts are the same. So the computer doesn't know, we haven't told it what to do. It doesn't know what to do when things are equal. We've only told it, hey, when it's positive, when it has more positive words, give it a P. When it has more negative words, give it an N. We didn't tell it what to do. It doesn't know automatically what to do in some situations. You, as the programmer, as the human computer scientist working on this, you need to tell it what to do. So in here, students can then create a label for that. So let's just call it, it's a mixed review if it has equal and positive and negative. So we're applying that label. And now you'll see that our undefined list is now labeled as mixed. Okay. So we can look at this and see how did the algorithm actually work, right? We can look at some of these reviews here and see if they make sense. So this one maybe makes sense. These have great traction. Playing Nerf basketball in them, kind of dangerous. Okay, that might be a mixed review. That sort of sounds equally positive, equally negative. Let's see. This one here. These slippers were terrible. They were so slippery. Every time I wore them in the kitchen, I slipped and fell, and it hurts. That sounds pretty negative, right? Right. Usually there's a lot that are really wrong. All right. Let's see. These slippers have great traction. I'm flipping them, I feel. All right. All right. Well, let's look and see. So we can look and see at the final results, and this will actually tell us. We then went through and actually labeled them as a human, comparing it to the computer. So the computer only got 48%, or 48% were incorrect. And so I just, when looking through, couldn't find one immediately to share, but this will tell me now which ones to share. So the guess label for this one was positive, but it actually was in a human-defined world. We would say this was a mixed review. And the results differ partly because how a human would label something is not how this very strict algorithm that we gave the computer doesn't always capture all the nuance with language. The human brain could consider context that something is put in. And so reading a review, that might help know whether something is positive, negative, or mixed, but the algorithm is only looking at the frequency of words. It doesn't have that same context being added to its guessing. So here we can see this one was labeled as positive. It guessed that this was positive, but it actually is a negative review. It's a little bit longer of a review. There's more words included. And so the computer tried to guess how many positive words, but it thought there were more positive words than negative words. But when you read this review, the slippers have no traction, especially not on a smooth vinyl floor. This morning after watering my plants, I slipped. I didn't fall, but I dropped the plant and the pot broke. I could have gotten hurt. I will never wear these slippers again. They are too dangerous. Is clearly a negative review. So we have some work to do for our algorithm. It is not solving all of our problems. It's not necessarily labeling these as we would like. So in the final script, students have the chance to refine the algorithm and see if they can improve the accuracy of the results. And so training a computer to recognize these positive and negative reviews, we're giving the computer reviews that were labeled by a human. It's using that data set to train the computer on patterns that it's seeing, and then it's using those patterns to guess whether the review is positive or negative. In this script, students are able to manipulate the machine learning algorithm, that algorithm that we're building, by using these sliders to change the amount of training data, the number of times a word needs to be repeated in order to be considered frequent, and they can remove and add words for the computer to think about or ignore. Okay, so students have time to iterate, test, and improve this model. I encourage you to go and try it out on your own after this webinar. I'll go through a few examples here just so you can see how it changes, but you can play around with this script for quite a while. So let's just start with those 48 reviews. That's what we were working with before. 48 reviews for training. Let's do seven repeats of a word to consider positive or negative. This is going to show us those histograms. So these are the words that appear in those 48 reviews that occur more than 7 times in positive reviews and in negative reviews. This is another way of looking at those lists, and then those common words are removed. And what this next part allows us to do is we can remove words that we think are not significant. So looking at this list, maybe I want to remove the word be. I don't know that be is a word that's particularly negative. And so we can do that. And so now we've removed that word be from the negative list. We've said ignore it. We don't think it's important. You could continue to do this. You could add more words. Let's just see what the algorithm does with what we've built so far. And in this case, the computer got 16 correct out of a total of 29, which is 44% were incorrect. That's not great. So let's go back and see if we can refine the algorithm and make it better. Okay, so we can go back up. Let's try training it on more reviews, right? That would make sense. If we're giving it more data to train itself on, to pick more words out of, that should improve our results. So let's say we're going to load 100. We're going to now look at 100 different reviews. So it's being trained on 100 reviews where a human has written positive or negative. Let's say we want less repeats. We only care if a word is frequent 5 times or more. So we want more words on our list to think about. Okay. And we can update these histograms and see now there's a lot more words we're dealing with. They're at a lower frequency, so we have to keep that in mind. There might be more to remove. All right, and now we can remove those common words. So our list just got much longer. Now we have a lot more positive words we think are positive, words we think are negative, and we've removed a lot of commonality between them. All right, so now we're going to fine tune. So let's see, again, A. I don't think A is a word particularly associated with just a positive review. So let's remove the word A. Okay, so now we've removed that. Maybe we want to remove some other words. Is, oh, that is a common word. Maybe we want to add some words. Maybe we think a positive word would be super, right? We think if a review includes the word super, that would be positive. We can add words, but the computer is telling us, oh, well, the word super wasn't in the reviews at all, so we don't know what to do with where that's not a word that we can look at. All right, so it has built-in checks in order to refine itself, but it has to be using the data that it was trained on. Okay, so we could continue to add or remove words. Remove B. All right, and these would all update. You can continue to do this and refine. Let's see how the algorithm did. All right, so now by using more training data and lowering the frequency of words, we got 20 correct out of 29 reviews, which is only 31% incorrect. So we improved. We were almost 45% at the first time that we're incorrect, and now we're at 30%. So you could continue to refine this, build an algorithm, that continues to improve. I will let you know that with reviews, only up to 140 reviews that we have, and given this type of machine learning model where we're just looking at frequency of words, you're not really going to get better than 80% correct or 20% incorrect. So that's one of the limitations with using this type of model. And so you can get to that point. And one of the discussions to have is that good enough? Does this simplified model, it's something that we were able to build in just a few minutes here, refine and work out, is that good enough for what you're trying to solve? Are there situations where that's definitely not good enough and we need to find new methods in order to improve that model? Okay. And so that would be those would be some of the conversations that would be had with the students, and thinking about how they can use computers to sort their positive and negative reviews so they can get that feedback on their slippers and eventually improve the design of their slippers as they continue to engineer new ones. So by the end of this module, hopefully students have a little bit more insight into understanding how simple machine learning models work. What we just did together, that was machine learning. That is a type of AI. Computational tools are powerful and they can really help you solve problems, but computers and AI can't solve them magically. There is a human component that is needed in order to make sure the right algorithm is being applied and the right training data was used. A computer might identify problems that that a human might consider irrelevant, or it might identify um, patterns that, or a human might think about patterns that a computer doesn't know to identify. And training data influences heavily what is learned by machine learning algorithms. And so the data that you put in, if that is wrong or biased, that is going to impact the algorithm and impact the machine learning, and that will be shown in the answers as well, in the solution as well. So it really needs to be thoughtfully assembled and quality that's being input into this algorithm. So they are powerful. They do require some work to make sure that they're the right tool and they work as expected. And so I'm going to pass back to Kendall to consider how students might take this experience, and where you can see those different computer science principles within this module.
Okay, so as we are thinking about user reviews analysis, these are the two guiding questions for that unit. The first being, how can we train a computer to label a review as positive or negative? Very simple. And then the second is, how can we improve the computer's accuracy of the computer's guesses? So if we're thinking about our framework here, generating and using algorithms, for example, training a computer to classify those reviews involves creating and using algorithms. These algorithms are processing data, identifying those patterns, and then being able to classify the review as positive or negative based on any of the patterns it's observed. And this, of course, aligns with that part of our framework on generating and applying those computational methods to solve problems. The next one, improving the accuracy of a computer's guesses, requires optimizing the algorithms to handle those errors and biases and the limitations of the training data. This reflects the goal of enhancing the efficiency and precision of those computational systems as highlighted in the framework. And of course, the last one, recognizing the social context when training a computer to label those reviews. Understanding the social and cultural context of language is really, really important and kind of difficult for a computer to do. For example, like sarcasm or idioms or even context-specific meanings. When when kids say it's mad good, it might be a little difficult for a computer to understand that. And that can really affect whether a review is genuinely positive or negative. And recognizing this aligns with the framework's emphasis on considering the social and contextual factors when designing some sort of computational solution. So, with that said, let's chat about our other middle school unit, which is engineering medicine coolers. So in engineering medicine coolers, the unit guides students through the engineering design process to create a medicine cooler that protects medications from high temperatures. Students explore thermal energy transfer by testing insulating materials and cooling solutions, and then they use their findings to inform their medicine cooler designs. They brainstorm, plan, build, reflect, and refine their medicine cooler prototypes. They record temperature data to evaluate how well this medicine cooler is performing. The unit concludes with students actually presenting their designs and reflecting on the engineering design process. And it actually culminates in a sale to very specific users who are looking for very specific design criteria, like very cheap or it cools really well, and they have different combinations of those. And they select the most effective solutions. And of course, it combines quite a few things, including science concepts, engineering, problem solving, etc. And for this, of course, there are also two computer science modules, one of which is medicine cooler alarms, where students actually start to think about, okay, we designed a medicine cooler. Now we need it to tell us when it's too hot, and we need to change out our cooling packs or attend to our medication, which includes developing an algorithm for a microbit. But the one we're going to talk about today is heat wave visualizations, which uses MATLAB to generate data visualizations for who might be most impacted by heat and might need this medicine cooler.
Great. So again, we are going to look at a few different live scripts, but this is a very different application. This unit takes a different approach to how computational tools can help engineers. So in this unit, as Kendall mentioned, students are thinking about heat waves and how people in different regions or different people are impacted by hot temperatures. They're using this computational tool actually in the frame step of the engineering design process. So as they are building their understanding of the problem that they're trying to solve, these tools, this data visualization is helping them to really think about the widespread geographic differences of temperatures and how different people might interact or might experience different heat waves. And so it's in the previous unit, it was more about informing design improvement, more about thinking about how to incorporate user feedback and improve your designs. More at the end of an engineering design process. This one is really at the beginning to gather data so you build your problem correctly from the start. So in this series of live scripts, MATLAB is used to explore data visualizations to show the number of heat wave days in a given weather station experienced in 2001. In this example here, we're looking at a map of the United States for heat waves that are defined as any day between May 1st and September 30th, where the high temperature was greater than 90 degrees Fahrenheit. This is what we are considering is a heat wave. So we can look at this map and you can again spend some time, I can put the link in the chat, exploring it on your own as well. We're going to move through this quickly. And you can look at different station information and data and explore different heat wave examples. So see, we're looking here at something in Oklahoma where they experienced 41 heat wave days based on the definition that we shared. Right? In Massachusetts, at Logan, that's where the station is located. There were 6 heat wave days in Massachusetts during that time. It also gives elevation data. So this code, this visualization is using over 800,000 pieces of data. So if you could just imagine what a spreadsheet would look like with 800,000 different data points for all the weather stations across the United States for 365 days a year, high temperature, low temperature, average temperature, elevation, station data, state data, all of this that's incorporated into this visualization here is a lot of information. And this is a much more digestible, easy way to see those results and explore it and investigate and look at this data rather than trying to understand a spreadsheet of 800,000 data points. But it really depends on how you build this visualization, and that's what students start to investigate with this. And so they then look at a second definition of what a heat wave be. So different scientists, engineers, um, different health safety folks, they all have sort of different definitions of heat waves. There's not one definition that everybody goes on based on what is a heat wave. It matters based on where you are geographically, what is normal for the area, what you're concerned about. Somebody, a health and safety wellness person might be in a located inner city, might have a different definition of a heat wave than somebody in looking at flora and fauna in the Amazon. So there's different definitions, and students start to explore how that can change the visualization. So this is a different definition of a heat wave, where it has to be greater than 105 degrees Fahrenheit for 2 consecutive days. The low temperature can't drop below 80 degrees between May 1st and September 30th. And so you'll see this is a very different looking map. There's a lot less stations that had heat waves based on this definition, but the same 800,000 data points is still being used in the background behind this to build this visualization. So students start to realize that the algorithm that you're applying to this data, how you're building the visualizations, that matters. And again, thinking about that human component, who built it, what they're building, that definition needs to be clear for you to start understanding and analyzing these visualizations to really understand the story that's being told. So we're going to jump to the more active live scripts for this one. There's a few others in the series, but we're going to look at creating our own heat wave definition. And we're going to build our own example. So here, students are given a script, and I will zoom out just a little. There we go. Students are given a script where they now get to build their own definitions. So they work together in teams to think about what do they think a heat wave is. And there are these drop downs for them to choose what they consider to be a heat wave. So let's say we think it's 2 consecutive days where the high temperature, they can choose high, low, or average. Let's say average temperature is greater than, I don't like heat, so I'm going to say greater than 90 degrees. Maybe we'll make it 3 days, okay? 3 consecutive days where the average temperature is greater than 90 degrees. Starting May seems reasonable, maybe going to October because it's been a lot of hot summers recently. All right, so we're going to set those parameters, and we can look at how our visualizations change based on the algorithm that we're telling the computer to use. Okay, so we can see here in this visualization, this is just telling us which stations had a heat wave based on our definition, which ones did not. So any in red, those had experienced a heat wave for average temperatures of 90 degrees for 3 days. So only 3% of our stations experienced a heat wave with this. We can then look at this in just a few different ways. So this is just starting to understand that you can present this data in a lot of different ways, and depending on how you present it might help you understand the data better or share those results with other people. So this is looking at the number of heat wave days. So this just said yes or no. This is now how many heat wave days did those stations experience. And then this one is a bubble plot. So it scales the size of the bubble based on how many days. So it's just a different way of looking at this data. We can also look at an animation of this. And I'm going to actually change the definition up here a little bit so we have a better, we have a few more stations that are being shown. So let's just say that it's 1 consecutive day, high temperature of 96 degrees. We can rerun the script. Okay, now there's a lot more stations. 47% of the stations experienced a heat wave with this definition. You can start seeing geographically where these are located, maybe as expected, more in our desert areas. But the high mountain region, those stations don't seem to have as many heat waves there, right? Our colder north, not as many heat waves. And then students can also look and see, and this will animate across the dates that we showed, and it will show you when the station turns red that day, they experienced a heat wave. So you can start to understand throughout the months that you're seeing, the days, you can actually see the timeline, right? Previous plots, we just added up all of those together. So if it had 14, we saw 14 heat wave days. This will actually tell us where across the months of May to October those 14 days happened. And so this animation takes a few minutes to run, but if you see a white circle, that just means we didn't have weather station data for that day, right? So we can't make up the data for that. We're just using the data, and you'll just see around July 25th, for some reason, a lot of weather stations for NOAA went down that day. And so there are some gaps in the data, but overall it gives you a sense of what this looks like throughout the entire, it could be the entire year, or in our case, May to October. So this will just run for one more second here. Should have shortened our window for just this example. But then at the end of this, students will be able to scroll and sort of look at the animation in more detail. And so that if they were interested in a particular day, they could scroll and see what a particular day looked like in terms of temperatures across the country for the different weather stations. So it's just different ways for them to explore data and also understand how the different definitions that they created and are looking at impact people across the country. And so here you can just kind of scroll through and see, visually maybe around July 25th, that's one of the hottest days across the country. We're seeing a lot of different heat waves. And then you can also see how it sort of migrates around the country, right? There are different areas of the country get hot at different times. So if you're thinking about designing a medicine cooler, where in areas where maybe it gets hot at different seasons, you can take that into consideration. Sometimes, heat waves are associated with rolling brownouts or blackouts, and you need to think about those locations, what their weather is at that time, to know, what their different solutions might be for storing medicine at the correct temperature. And so the final script allows students to look at smaller data sets, just looking at it in geographic regions, so they can sort of zoom in on just a different climate region. They could look at the Northeast, they can look at the South, and they can sort of do a little bit of a deep dive in maybe the states and regions that they're more familiar with, or do a deep dive in an area where they're not familiar and sort of see how different things are. And again, they can look at the elevation that can impact why some states, some areas might be having a heat wave and others aren't, what's coastal, so they can start sort of teasing apart why they might be seeing some heat waves in areas that they're not seeing in others. So at the end of the module, students think about what a heat wave means to them, and then how their personal experience might result in different definitions and end up then creating different visualizations. So what they think is hot might not be what their partner thinks is hot, might not be with what students across the country think is hot. And so they start to think about that, think about access to AC, pools, buildings, tree coverage, all of those things might impact what you think a heat wave is. And so each of these lessons can then also be linked back to the computer science framework. And so I'll pass it back to Kendall to sort of pick apart and show you where those are applied in this unit.
Yes. So to sum up our heat wave visualizations unit, again, here are our three guiding questions for this module. How can visualizing heat wave data help us identify which regions and people might be impacted by hot temperatures? This one really has some overlap with a few of our principles on the framework. For example, it does tie into the creation and application of algorithms that analyze the heat wave data to generate those visualizations. These algorithms obviously process a large data set to identify those patterns, such as areas with the highest temperatures or populations most at risk. And that makes the data more actionable for students to apply it to who might be most impacted by heat and what are their needs when I'm designing my medicine cooler. So it also overlaps with the recognizing social context. Now, the second question, how can the same data be used to create different visualizations? Of course, this also has some overlap in a few different things. Not only does it highlight that we need efficient tools that can transform the same data set into various visual formats that make it easier to digest, but it also tells us that we need some accurate representations, that there are many definitions definitions of heat waves that can be defined in many different ways, which allows students to think about the social context, and just the general context as well. If, like Mary had said, if you're a climate scientist studying climate change in Alaska, you're going to have a different definition of a heat wave than somebody in the United States studying different animals in the Southwest region, for example. In that last question, how does an individual's perspective influence a data visualization? Of course, is really the core of this module, and really asks students to recognize social context in a very specific way. It emphasizes how the interpretation and presentation of data can vary based on all sorts of things, whether it's cultural, professional, or personal. Like Mary says, I don't like heat, and changes the temperature. That can change your entire data visualization. We want students to recognize that and walk away knowing that something as simple as preferring warm or cool weather could change the data visualization, and that biases aren't necessarily always bad. Sometimes it's as simple as a preference that can really change our data and change how we use that data if we're changing our definitions and those biases are playing in. So, with all that being said, we're coming up right at 8 p.m. And we really hope that you enjoyed listening and sort of got a better sense of how engineering and computer science can be paired together, and really start to understand how powerful the tool MATLAB is, and how it can be used in the classroom to really help students develop their engineering skills